Hello and welcome to Lecture 5 of Math 2R03. So in today's lecture, we're going to look at Section 2A of the textbook, in particular about the span in linear independence. So the goal of this particular section is to introduce the notion of span and linear independence in a general vector space. So you've actually seen these topics before when you took Math 1B03, but the focus here is to kind of extend it to any particular vector space. And in today's focus is really actually only on the notion of span. And in lecture 6, we'll follow up by finishing section 2.8 and talking about linear independence. So again, to reemphasize, today's focus is going to be on the span of a collection of vectors. So first, let's talk about the span. And in order to talk about the span, we have to talk about a linear combination of vectors. Okay, so and again, this is something you may remember from Math 1B03. So a linear combination of vectors, V1 through Vm, in a vector space is a vector of the form A1 times V1 plus A2 times V2 all the way up to AM times Vm, with each of these AIs belonging to your field F, where F is either the real numbers or the complex numbers. So that's just what a linear combination of the vectors is. You just take your vectors and you add them, you take scalar multiples of them and you add them all up. Okay, so as a simple example, here's two vectors in F3, and I'm going to take 2 times the first vector plus minus 1 times the second vector. And so let's figure out what this is. So 2 times 1, 2, 3 gives me 2, 4, 6. And then multiply the second vector by negative 1 gives me minus 2, minus 4, minus 7. And when I add these two vectors together, I get 0, 0, and negative 1. So this guy right here is a linear combination of the first two vectors, right? So this is a linear combination of the first two vectors. Okay. And now what we want to do when we define the span is basically we want to take a collection of vectors and then take all the linear combinations of those guys. And that's what's going to be called the span. Okay, so the span, given a set of vectors, v1 through vm and v, the span of v1 through vm, denoted span, v1 through vn, is the set of all linear combinations of v1 through vm. Okay, and if you prefer to use set notation, what this means is the span of v1 through vm is everything that looks like a1 times v1 plus a2 times v2 all the way up to am times the vector vm, where the AIs are free to run over your field. Either it's the real numbers or the complex numbers. Just one piece of a notation that sometimes will pop up in the book. If you take the span of the empty set, we would consider that to be the vector space containing just a zero element, or in other words, the trivial element. Okay, and kind of to tie back into this particular example up here, we have that the vector 0, 0, negative 1 is inside of the span of the two vectors 1, 2, 3 and 2, 4, 7, right? Because this vector, as we saw, can be written as a linear combination of these two vectors. So we have a theorem here which tells us something about a span, and namely, if we take any vectors v1 through vm inside of V and we form the span of those vectors, we actually get that the span is always a subspace of V. So this is great. We can take a collection of vectors, form its span, and build something that is a subspace inside of V. And the second part, the useful property, is that when you take the span of V1 through Vm, it's actually the smallest subspace inside of V that actually contains all of V1 through Vm. So if you're given a collection of vectors and you want to know, okay, what is a subspace that contains it, the span is the smallest thing that contains those guys. Now, the proof of A, because it's checking that it's a subspace, really boils down to checking the three conditions of being a subspace. So I'm actually going to pause here and give you a chance to think about the proof of this. I've actually started the proof for you. I've already shown that 0 is in the span, and that's pretty straightforward because 0, you can write it as the scalar 0 times v1 plus the scalar 0 times v2 and so on. So the vector 0 is in the span. But what about the other two conditions? So after the short break, we'll come and we'll finish up this proof.